All right, hello everyone, and welcome back to Kareem's Chemistry Corner again for the rest of the semester. Because you have your exam coming up on April 13th, we're going to do a review on a lot of different topics that you guys have covered throughout this unit. So I'll just show you what those topics are first, and then you can feel free to skip ahead or do anything if you don't want to review a certain topic. So we're going to do quantum numbers. We're going to do electron configuration and oxidation states. We're going to rank things by their electronegativity. We're going to rank them by their atomic radii and their ionization energy. And then we're going to finish off by doing Lewis dot structures, geometry, polarity. And during this unit, I'll probably also talk about sigma bonds, pi bonds. And I think that's about it. I think that's all you guys really talked about. If you have other questions, please email me about this stuff, okay? And I can try and give you a good email explanation, or I can maybe make another small video for you just to explain something, if that's necessary. All right, so let's get started with quantum numbers, since I think this one is the most straightforward, although it seems like it's kind of challenging. It really isn't. It's very simple, and it's really just a way for us to locate electrons. So what we're doing is we're actually locating where is the valence electron, or valence electrons, for these particular atoms. So that's what we want to do. And what I also have with me is one of these. So you also definitely want a periodic table on hand, because this is what you're going to use to actually make those determinations. Okay? So I'll just keep this off to the side and I'll bring it up whenever we need to. All right, so for carbon, let's get started. For carbon, we have an N value, an L value, M sub L value, and then an M sub S value. And so for carbon, the N value, which is the energy level, if we look at our periodic table, it is in this period, or this row. So that's actually an energy level of 2. So the N for carbon is going to be 2. Okay, L refers to whether it's an S, P, D, or F orbital. And they are increasing in energy in this direction. So the way we express that is we assign S as 0, P as 1, D as 2, and F as 3. So in this case, if we look at our valence electron for carbon is here, in this specific spot in the periodic table. So this is the P block. So because it's in the P block, our L value is going to reflect P. So L is equal to 1. Okay? Now M sub L is the the M sub L value is the position that it's on for a particular energy level. So if you're looking at an orbital diagram and we have P, we have an M sub L value of -1, 0, +1. Okay? And so what we're looking at is, where is this electron? Is it here? Is it here? Or is it here? Okay? So when we're looking at that, we bring up our periodic table again. Sorry for the interruption earlier. I hope that doesn't happen again. If we look at our periodic table, then we can see carbon's here. And so this is going to be, if we're drawing that orbital diagram, this is going to be this position, right? Because we start drawing this way. So we go 1, 2, 3. So if we're going in that order, we would go 1, 2, and we would not have this one. Oh no, I closed my periodic table. We'll just pull up this one. Okay. Here's a slightly different looking periodic table, but I accidentally closed the other one, so we'll just use this one. It doesn't really matter. Okay, so we have that right there. So that means that this is the electron that we're talking about. Okay, so that means our M sub L value is going to be 0. Our M sub S value refers to the spin. So the spin in this case is upspin, because we've drawn it in this direction. If for whatever reason we'd filled this orbital, or we'd filled it with all upspin, and then we started doing this, and then for whatever reason it turned out to be that electron, then it'd be downspin. And so the way we represent the upspin electron, which was here before I drew over it, is we represent it as plus 1/2 because it's upspin. If it was negative, or if it was downspin, it would be negative 1/2. Okay? But in this case, it's plus 1/2. And we'll see that maybe in the case of nitrogen. No, we will not see that in the case of nitrogen. Maybe phosphorus? Nope, also not in phosphorus. Just take my word for it. If you have 1, 2, 3, if you fill, I guess if you had fluorine, for an example, fluorine would give you an M sub L value of right here. So give you an M sub L value of 0, but it would be downspin. And so that's a distinctly different electron, and that's why we're using quantum numbers to locate that specific electron. Okay, so let's go on to nitrogen. So nitrogen is actually neighbors with carbon. So that means that we're going to have 1, 2, 3 in our orbital diagram. N is still going to equal 2. L still in the p block, so it's still 1. M sub L, though, now is no longer 0. It's actually plus 1 because this is the electron that we're talking about. This was carbon's electron here, and this would be boron's electron here. But boron is actually a weird atom, so we're not going to talk about that one right now. Maybe more to come on boron later. So our M sub L value is going to be plus 1 in this case. And then our M sub S value is still going to be plus 1/2 because it's still upspin. Alright. Phosphorus, same thing. It's underneath nitrogen. So what that means is that it's going to have a different N value, but still the same L value. So N will equal 3 now because it's a row down. L is going to equal 1. It's still in the P block. M sub L is going to equal 1, 2, 3. So if we're following the same logic, right? Let me pull this up again. So if we're going 1, 2, 3, then we're doing 1, 2, 3. We're still talking about that electron. So it's still going to be plus 1. Okay? And M sub S is still also going to be plus 1/2. Okay? Let's see if I can adjust this up a little bit like that. All right, and so this is the way that you do quantum numbers. All right, and this is the electron that we're locating. So that's what a quantum number tells you. But for phosphorus, there is one electron that is the outermost. All right, or there are a few actually that are valence electrons. But it is the last electron that we're talking about when we say quantum numbers for nitrogen, carbon, phosphorus. Okay. All right, so that's quantum numbers. Again, let me know if you have questions about that, either by email or in the comments. Email is probably better because I don't really check the comments. But yeah, it's up to you. All right, let's move on to electron configuration, which is a little bit different, and also determining oxidation states based on that electron configuration, because determining those possible oxidation states is going to depend a lot on that configuration. So let's talk about vanadium first. Okay, so where's vanadium at? Vanadium is over here. Vanadium is right there. So let's do that electron configuration. I'm just going to do it with my finger here, and then I'll write it down. All right, so it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3, right? 3d3, because that d orbital has one lower energy level. So let me write that out. So we said 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we have 3d3. And if you have your own periodic table, you can follow along. Okay, so this is the electron configuration for it. The abbreviated configuration for it would basically just start you off with argon. So that would be, let's see, argon would basically go here. And then you would not have the rest of it. Okay, so you just have argon and then this, and that would be it for the abbreviated one. But I'm going to do the full one just because that's, I think, maybe more useful to everybody. Potential oxidation states. So when we think about oxidation, we're thinking about electrons being removed, right? So the question is what are the possible oxidation states that vanadium could actually exist in? So we're not saying what is the state, but what are the states? What are the possible states? And the way we determine that is based on these electrons right here, the valence electrons. Now, you might be tempted to remove this 3d3 because it goes in the end. But this 3d3 actually has less energy than the 4s2. The 4s2 is actually slightly farther out, and so it's going to get removed first. So we can think about this as removing electrons by orbital. Okay, so if we remove a 4s2, and I'm just going to write this in the NLX form here.